if a PhD from India can pave way for
Dear participant, wait for a while. There's a little technical error. Ma'am, you can unmute now.
Okay. Yeah. So I don't know what happened, but I got disconnected from the meeting. Okay, I will reshare and start again. Okay, can you see my slides and hear me now?
Yes, ma'am. You are enough clear and we can see the slides.
Okay, so I will quickly begin again. First of all, I would like to thank the organizers and Dr. Shubhangi Rath Kantiwar for inviting me to speak at this development program and to be speaking amongst such illustrious people, all of the stalwarts who have graced the development program over the last 4 days. It's truly a privilege and an honor, and thank you so much for that. I also want to thank you for such a kind introduction. As you mentioned during my introduction, that I recently graduated with a PhD from the Indian Institute of Science and made a transition from academia to industry. This essentially would be the essence of what I'd be speaking about today. And as opposed to some technically heavy presentations that you might have seen over the last few days, this one is going to be a very light interactive presentation. And I would like to keep more time towards the end for questions. As I said, I have very recently made the transition, so I might not be the best person to talk a lot about it. But since the experience is very recent, I think it could be of help to a lot of students, and it could also be very helpful to our faculty members in kind of tuning the curriculum or kind of tuning the teaching methods to make our students more suitable and more comfortable and more confident to apply to these industrial positions, because as I'll be speaking about in the subsequent slides, we do see a barrier. So the transition from academia to a different academic position is pretty routine for PhD students, but the one from academia to industry is not that common yet. And that is because there is some inhibition in the students, as well as they do not get the kind of support they should from their advisors. So I would like to touch upon a few topics through the course of this presentation, and then towards the end, we could take up some questions, and I'll try my level best to answer them to the best of my ability. A brief introduction about myself. I recently, as I said, graduated with a PhD from the Indian Institute of Science in Bangalore. And in February 2022, that is early this year, I joined Infineon Technologies in Villach, Austria, as a senior technology development engineer working in the field of gallium nitride. I will be speaking more about what I do there. So without further ado, I would start my presentation. First of all, I'd like to, begin by sharing a very simple, description of what a PhD essentially is. It is, of course, one of the most regarded academic degrees. But what a PhD degree essentially results in, or must result in, is an independent researcher, a researcher who's, capable of, addressing a scientific problem independently and coming out with innovative solutions for that problem. It should transform a student to a professional who has a diverse set of transferable abilities. That is, abilities or skills that are not only suitable for a given research problem, but skills and abilities that could be used at any research problem the student or the professional wishes to tackle in their lives after PhD. And finally, in the research domain in which a candidate, he or she does his or her PhD, they should have an in-depth knowledge of that research domain, and they should essentially be the masters of that domain. So now, if you come to think of it, it is such a specialized and respected degree. But if you look at the numbers, you would not imagine that there is a huge number of PhD degrees that are awarded in India. So this is the number for India, and the source for this is the University Grants Commission. The graph here shows only the numbers till 2016. I will quickly put up my pointer. The numbers only till just 2016. But if you look at the total number, which is like the blue bar here, you see that in the academic year 2015-16, there were about 27,671 degrees awarded, and which is almost the double from the academic session 2007-2008, which means that in less than a decade, there's almost a double in the number of PhD degrees that are being awarded in India per year. And if you now look at this number, and this is the very recently released number by the University Grants Commission, in 2020-21, this number has increased to about 38,798. So about 40,000 students graduate with a PhD degree each year. And last year, essentially 40,000 students graduated with a PhD degree. And if you compare these statistics to what happens worldwide, you'd see that, India in 2015 was only, fourth to United States, Germany, and the United Kingdom. But if you look at the current statistics, which are not shown in this graph, India has actually come at par with Germany. So it's only now second to United States in the number of PhD degrees that are being awarded per year. So there are a large number of PhD graduates per year. Let us now look at what essentially the challenge is. I think every PhD graduate and all of you faculty members who have been through this experience can also probably relate to the fact that once you are towards the final years of your PhD, there is a question that starts, bothering every final year graduate student. And that question is, what essentially should I do after my PhD? Do I have limited options to choose from? A quick answer to that would be no. There are an unlimited number of options a PhD student can choose from. But of course, the question as to what I should do after my PhD is a difficult one. And there was a recent survey that was conducted by the Indian Institute of Technology in Delhi, IIT Delhi, in what PhD students in India, basically the preferred career paths PhD students in India would want to go to after their PhDs. And this is kind of reflected in the pie chart here. So I'd like to spend like a minute or two discussing this because this essentially forms the base of my presentation. And if you see the blue pies here, essentially the blue sections of the pie here, they basically refer to the faculty position. Basically, a faculty position in research means that the individual wants to join a university and wishes to continue doing research. They want to set up their own research lab in addition to teaching. The smaller blue color here basically tells that there is also a large fraction of PhD graduates who wish to pursue teaching positions. So they do not want to essentially set up their own research labs, or they do not essentially want to pursue research, but they wish to join an engineering college or a science college or an IIT or an IISc only for a teaching position. And then there's also a large section of PhD graduates who are interested in looking for government jobs in research labs. So basically these three career paths after PhD kind of hold the maximum weight, and these are the most preferred ones for PhD students within India. The next after this, of course, is postdoctoral studies. So a lot of PhD students also wish to continue with their research work, and they wish to pursue postdoctoral studies in the same field or a different field than their PhD research work. But if you now look at the small section here, and these are results just for India, just to be clear. So if you now look at this small section here, there's only like about 2% of people who want to, contribute to scientific communication. So basically become writers or columnists, writing about scientific topics in newspapers or in magazines, or in scientific communication. What also counts is that you could act as editors for papers, like for manuscripts. There are companies in India that help students whose native language is not English. None of our native languages is English, of course, but there are students who are, of course, not comfortable with English. So there are, companies and websites in India who help students like these they help polish their manuscripts for them. So there are also job opportunities there. And there's about 2% of students who wish to go for scientific, a job in scientific communication post their PhD. Some of them, of course, dream to have their own startup based on the work they've done as a part of a PhD, and also based on the networks they've forged during their PhD years. There's also like about 5 to 6% of people who are interested in holding a consultation position. So they want to, offer some sort of a career consultation post PhD. And then, of course, there's about 10 to 20% of people, but not a huge number, which is the dark green section here, which are interested in going for an industrial position. Now, the message that I want to kind of drive across through this slide is that if you look at the blue colors here, the blue sections of the pie here, these are essentially the jobs in our IITs, in IISc, in the ICERs, in all of the central government universities, in the private universities. These essentially encompass to positions at these universities as well as in the government research labs. Now, let us look at the number of positions or number of vacancies that are generated in these universities per year. So if you look at the number of positions that are generated per year, and you just look at the red numbers here, this is for all central and non-government universities, all private and central universities. And this is kind of a reflection of the number of vacancies that were generated in 2018-19. So the academic year 2018-19, there were about 1,262 positions for the post of a professor, about 2,000 for an associate professor, and about 2,000 for an assistant professor, which and for a fresh PhD graduate, of course, the position that they would be most interested in would be that of an assistant professor. And if we see the numbers, just barely 2,000. And if you now look at the number in, number of vacancies in government jobs, for example, that's also close to about 3,000. So if you now total, in total, just add these numbers, you see that there are about 5,000 to 6,000 vacancies generated in India for these positions per year. And the number of PhD graduates, as I talked about in the initial slides, was close to 40,000. Or if you look at 2018-19, that was about 25,000. So basically, there are 5 times the number of PhD graduates, and the number of vacancies in faculty positions or in government jobs is actually very dismal. And this is the motivation to kind of move towards alternate career prospects. I think a lot of people, and this is solely based on my interaction with a lot of my colleagues and my peers, a lot of people wish to continue in academia because, while they work on their PhD project, and while they have been in academia for a really long time during their graduation, their post-graduation, and then during their PhD degree, they get comfortable in the academic environment, and they also kind of fear to get out of the academic environment and explore new prospects. But since the number of positions is, the number of vacancies is considerably small compared to the number of PhD graduates, it of course makes interest to look towards alternate career prospects. That kind of brings me to the first prospect, and I would be spending a considerable amount of time talking about this one. A lot of people are of the opinion that in industrial position, you are expected to do routine work. And most of the PhD students, I think they get very used to research and development, and they get very used to working on innovative problems. So for a lot of them, what they feel is that working in an industry is a very routine, mundane job, and it's more like a 9-to-5 job in which you would not have a lot of R&D work to do, or not a lot of research and innovation to do. And that is why the inclination towards an industry position is abysmal. But if you actually look at R&D positions within the industry, there are a considerable number of research and development positions within industry today. And through this slide, I just want to compare compare how academia looks, which is the left side here, and how an R&D position within industry looks like. So when you're doing like your PhD degree, or you are doing a postdoctoral fellowship, you have complete scientific freedom, which is, I feel, one of the best things about holding an academic position. Even when you are a faculty member at a university somewhere, you have complete scientific freedom to explore whichever research problem interests you. Of course, the limitation there is to get the setup and to get the infrastructure to conduct research on that topic. But again, that's definitely a secondary thing. But as far as the choice for the research problem goes, you have complete scientific freedom to choose whichever research problem you wish to work on. The second thing that I think is the most exciting thing about academia, and something that I personally enjoyed the most, was it was not time bound. So I had my own time to explore different innovative solutions for my research problem, and there was no time limit for me to, there was no deadline within which I had to say get to a particular solution. And that also gives you a sense of independence and freedom, because then you can, of course, try many new approaches, and you can try different ways and methods of doing the same thing, and you can come out with innovative solutions for the same problem. And that is, what paves way for progress in a certain field. So, of course, these are the two most interesting things about pursuing a career in academia. The other thing that's very good about an academic position is that it's a proof of concept problem solving. And finally, an academic position is, I believe, very instrumental in building your soft and technical skills. So once you graduate out from your PhD, not only do you have a significant amount of technical expertise, but you also have a great set of soft skills that you could put use to in any environment that you go to. And that, of course, is a benefit, because you spend so much of time working on the same problem, and so much of time honing your own skills and honing your own confidence about a certain topic, that you do develop a lot of skills and expertise. And that, of course, is very instrumental in whatever career you decide to choose. As opposed to that, if you look at a career in industry, an R&D industry, the interests are broad. The interests are not essentially, the interest you have with your research problems. For example, if I am working on a certain problem, my focus would be on that problem. And that problem could be scientifically or technologically relevant. It might not be technologically relevant, but it, in either way, is, a scientific topic or a research topic worth investigating. In industry, however, the interests are broad. Whatever problem you're working on should eventually result in some sort of revenue, and it should be profitable to the industry in some form or the other. So, of course, there is a brief amount of restriction that comes in the in the research problems you can choose, and there is not the kind of complete scientific freedom that you see in academia. But the great part about being in or having an industrial position is that you actually have the opportunity to make a difference. You can also do that, while being associated with academia. And I always believe that these two things go hand in hand. Even with an industry, if many of you might already know this, but even with industries, a lot of innovative solutions are things that come from academia. There are academic collaborations. Each industry has collaborations with certain universities, and those universities and the PhD students working in those universities are essentially supplying the industries with innovative solutions, and the industry is only kind of optimizing it to get the best result and the most profitable result. So, of course, there is a strong collaboration for all big industries. There's also a strong collaboration with academia. But with industries, since there is a larger amount of funding and there's like probably a better infrastructure, there's an opportunity to make a difference. And you could, whatever research you do or whatever work you do, you know that it will translate eventually to a device that, a consumer, a device that the consumer would be using at the end of the day. Another thing that's very different in industries from academia is that in an industry, the focus is on team targets. So you work as a team, you work together as a team, and the focus is less on individual achievement. So it's more about working together in a team to get to a certain, there can be a time, there can be a milestone that the industry wants to achieve, or there is like a new product that the industry wants to come out with. And you work as a team. So the entire onus on the project being successful or not is not on you. It can be a good thing, and it, for people from academia, they often struggle with the fact that in academia, they're so used to their freedom, that they're so used to being their own bosses, that at times when you have to work in a team and when you, sort of have to convince the other people of what you're saying, they find it difficult to do. So that's also one significant difference between academia and industry. And finally, the scale and magnitude of things is very different. So if you compare, for example, I'd be showing in the subsequent slides, the scale at which you conduct your research, when you, for example, if you're doing a research in device physics, or if you're doing a research in semiconductor device engineering, for example, even if in academia, or while you're doing your PhD, even if you have like a handful of good devices, it's good enough to, to basically to confirm a proof of concept, or to basically get a publication for your work. But in an industry, what matters is yield, what matters is productivity, and what matters is how many devices. You want the least number of devices to fail. The scale and magnitude of things is completely different. So of course, there are a lot of new skills that you can learn there, of course. But as I said, the scientific freedom, that is not exactly as much as it is there in academia. The thing that I probably like the most about industries, or an industrial position, and which is also something that motivated me to make this transition, and that was essentially one of the major motivations to make this transition, was work-life balance, which I believe is very important. I can speak from my experience as a PhD student. I had no work-life balance. Not that I only worked and did not enjoy my life, but of course there was no structure or no system to my day. I used to wake up late. I used to work late at night. Of course, there's no deadline and there's nobody stopping you from working at any time of the day and so on. So you can just continue. You just go on and on and on about it. And there aren't essentially too many deadlines within which you have to finish your work. But then you are your own boss, as I said. But when you're working in an industry, as I said, you work as a team. You work with a team. So you have to kind of adhere to the overall working environment of the place, and you have to kind of structure your day like that. And that allows you to maintain a work-life balance, which I feel is very important to have a good quality of life. With industry also comes a lot of networking, and you have the possibility of interacting with a lot of people from within the industry who are working in completely different research problems as you, who come from completely different backgrounds, and that also teaches you a lot. When you are in academia, your interaction is mostly with your peers, or with your research group, or with your advisors, or maybe a few other people beyond your research group. But in an industry, you have the flexibility of interacting with multiple people who come from different backgrounds. And you also have the possibility of exploring different things. Your main project could be something that you're very good at, but you could always have, and it is a routine practice in industry, to have the possibility of having, alternate small projects that you are kind of learning. And those projects are not essentially something that you could, take care of independently, or take care of. They would need essentially a lot of training from other people who have been working on those projects for long, but you can, of course, be a part of project that you know nothing about. And that is something that's really very important if you look at in the long run, because that is how you learn new things. That is how you explore what you are good at and what you're not. If you will not work on diverse topics, you would never know what your niche exactly is. In addition to that, there is, as I said, fixed time hours. There is, in academia, of course, there's no limitation to the number of working hours, but in industry, typically your contract sets the number of working hours that you have to do per week. And for example, the industry that I work in, I'm not allowed to work more than 10.5 hours per day. So if by chance, if there's a lot of work, or if for some reason, if I am still in the transitioning phase, so if there are a lot of trainings, for example, and if I end up exceeding the 10.5 hour timeline one day, my manager gets a notification. And if you get it for like more than 3 days in a row, it adversely affects my professional growth, because they perceive it as a threat to your health, and they put a lot of emphasis on that. In addition to that, you can give a good amount of time to your family. An industrial position also typically pays more than an academic position. And then you also have certain number of vacation days per year, which is always a plus. So now I will move on to what exactly counts. So when you have to make a transition from academia to industry, for example, if something about an industrial position fascinates you, and if you decide to make a transition from academia to industry, what essentially are the skills that would be needed? I meet a lot of PhD students who are very hesitant to make this transition, and they often use their PhD as an excuse. So I read this quote somewhere, that you should not use your PhD as an excuse. You should instead use it as a lever, because as I said, your PhD teaches you a ton of soft and technical skills. For example, when it comes to soft skills, you get a willingness to learn. This is also something that your PhD teaches you. You become willing to learn. When you join an academic institution for your PhD, typically you know nothing about the problem that you would be working on. Very few people know something about the problem they'd be working on. And most people, start off as a clean slate. I would be talking about my transition, but I knew nothing about the research problem that I worked on, and absolutely nothing about, nanoscience and engineering for that matter. I came from a sciences background and I did a PhD in engineering, so I did not know anything. But what counts is the willingness to learn. If you're willing to learn new things, if you're willing to, if you have the resilience and patience to give yourself the transitioning time when you make a transition, any transition, it takes time to kind of settle in the new environment, and you should be resilient and patient enough to give yourself that time. You cannot expect quick results. You cannot expect that when you go from, when you join an industry after a PhD, within the first 2 months, you would be doing some work that would in some way be contributing to the end product. Most of the times, the work that you do, for example, I joined about 3 months back, and as I said, I'm still in the transitioning phase. I'm still learning new things every day. There are about 200 trainings that I'm expected to do. Out of those, 100 are for new softwares that I'm expected to learn, and 100 are for new basics that I'm supposed to learn, or certain scientific things that I'm expected to get better at. And in parallel, of course, my work is also going on, and in some way or the other, I'm also contributing to my team. But of course, that is also with a lot of guidance from the other members in the team who have been a part of the team for long enough. But I have to be resilient and I have to be patient during this transitioning phase. Also, as I said, you need to know how to work as part of a team. You cannot, in an industry, you essentially cannot work alone. And it does not work like that at all. You have to know how to work as part of a team. While you have to work as a part of the team, you also have to be self-reliant, because each member of the team would have their own topics that they're working on. So you cannot be too dependent on them. Of course, in the initial few months, as I said, you are made available all the help. But it is very important to also use those 6 months of training or the first few months of training very efficiently to learn as much from your team members as possible, and then eventually become self-reliant, because then you would be responsible for a certain very important part of the project, and you not doing your work properly can affect the progress of the project, which is something that is not very appreciated in an industrial environment, because everything works with a deadline and everything has a definitive milestone. And with that, of course, what becomes very important is time management. As I said, you do not have the flexibility of working around the clock. So you only have a certain number of hours per week, and you must know how to efficiently work within that time, efficiently network during that time, because it's not just about the work you do, it's also about the connections you forge and build while you are associated with an industrial position, because they, transform you as an individual. In addition to that, it's very important to have good communication skills. So it is very, very important. And I think these 3 points I'd like to discuss together. You should be empathetic and respectful towards people. You should know how to resolve a conflict. If there is a conflict at workplace, either it is, on the technological front, or if there is, an ideology that you do not agree with your peers or your team members, for instance, you should know how to resolve that conflict. And for that, it is very, very important to have good communication skills, to be respectful and empathetic while still making your point. And that is something that you only learn, I think, from being in an academic environment when you're working with diverse people. And when you work with diverse people, for example, during my PhD, I worked with a set of diverse people who came from very different backgrounds. I came from a background in physics, as I said, and my way of looking at things was very different from other people who were material scientists or who were, engineers for that matter, electronic engineers, and so on. So everybody comes from a different perspective. And if you want to be heard in a largely diverse team, you want to have good communication skills. And lastly, what is very important is that you should have the ability to take criticism, because especially for industries outside India, there is this tendency that, people, when they are at work, they tend to be very professional. And there would be times when they would criticize your work. That is not because they do not like you on a personal level, which is a very common thing, I believe, for Indians to think. Like, that's also the first thing that comes to my mind, if I can say so. If I see somebody criticizing my work, I think the first instinctive reaction is, does the person not like me? But you have to get over that, mental barrier, and you should have the ability to take criticism and, kind of transform that constructively to the end result. Similarly, you need a large set of technical skills as well. You should be able to come up with innovative solutions to complex problems. Very importantly, you should be adept with the latest technological developments in your field of research. We always talk about coming up with innovative solutions, but a lot of times I have seen PhD students and even professionals in industry not knowing what is already existing in literature in that field. You cannot set like a huge set of experiments without knowing what is existing in the literature. And if you do that, you're essentially reinventing the wheel. So that does not make a lot of sense. You should kind of, irrespective of the amount of work you're doing on the technical front, you should not lose sight of the bigger picture, and you should not lose sight of what is happening in the literature. What are the current trends, for example? What are, the most used or the most efficient methods that are being used for a certain characterization, for example, in the in your field of research, for example. So you should be adept with all those technological developments. And lastly, you should know how to draft and manage your project. You should know how to cohesively collate every every observation that you see. You should be able to cohesively draft it in the form of a presentation, in the form of a document, so that you can convey it to your other colleagues. Because what happens in an industry is that people keep switching teams. I might be in a team today, but 2 years down the line, I might decide that something other interests me. And if I have not documented the work I've done over the last 2 years properly, the person who comes after me might not know what all has been done. And of course, every team member, as I said, has their own responsibilities. So they might not always be able to fill in the new person always. So you should know the skills, and you should have the requisite skills, and you should learn how to draft and kind of cohesively collate everything that you see from your experiments, everything that you see from literature, so that the person who joins after you knows what has been done, and then they can of course take up the work from there, and the work that way is very efficient. Okay, so before I move to the next slide, this is kind of something that covers for me the motivation And now I would be talking about, as I said, these are the skills that essentially count, and these are the skills that you need to kind of make a transition from academia to industry or to excel in an industrial environment. And in the subsequent slides, what I would be talking about essentially is my experience, my academic training, my training over the last couple of years that, have been very instrumental in me being wherever I am today. So to begin with, I would like to kind of take you along, a walk through my journey. I was born in Haryana. I was born in Haryana, which is very close to the capital. And that's where my home is, and that's where I did my schooling. I was the head girl during the primary, senior, secondary, as well as high school. So I held the position 2 times in like 10 years. And that, and why I am mentioning that, a lot of people I do not see most people talking about their school life, but I believe my school life has been very instrumental in developing a lot of soft skills in me, especially, the confidence to conduct myself in front of a large audience, for example. That is not something that I've learned a lot in my college. Of course, I, took whatever I learned during my school life and, always that always kept translating to a better confidence in front of the audience in over the subsequent years. But of course, the foundation for that, if I may say, was established during my school life, and I am forever indebted to my school for that, because I was, very active in curricular as well as co-curricular activities. So I believe that also plays a very important role in shaping you as an individual and in developing a lot of these soft skills that I talked about in the previous slide. After my schooling, I did my graduation and post-graduation from University of Delhi. So I was affiliated with Miranda House, which is a girls' college in University of Delhi. And that is where I did my bachelor's, BSc honors in physics and MSc in physics from. So this essentially, forms the first phase for where I started developing a lot of the skills and kind of also developed an inclination towards research. So I would like to, at each of these timestamps, I'd like to kind of spend a little bit of time on what exactly was about these places and what exactly these places taught me. So when it comes to Miranda House, it's a college that's recognized a lot for its beautiful building and these alleyways, and of course this beautiful, ancestral sort of canteen that you might have seen in some movies. But for everybody who's been associated with Miranda, I think especially over the last 4 years, for example, Miranda for them is the All India Rank 1 college as awarded by the NIRF ranking. So consecutively for 5 years, right from 2017 to 2021, Miranda House has been ranked as the best college. And that is for a reason. I have always shared with my peers that I had the best teachers. I never felt that I was in a college. It almost felt like a school because everybody was so particular about what we were doing. And, at that moment, you do not like that much, because when you kind of move from, your school to college, you expect like a fun life, you expect a lot of societies. And when, you talk about Delhi University, you expect your life to be very happening. But when you are in a college like Miranda, it gives you enough opportunities to excel even co-scholastically. I wouldn't say that there weren't any co-scholastic activities, and I was also associated with a lot of co-scholastic activities. But when it came to curriculum and when it came to, our courses, our teachers were extremely particular. And, it was very rare to, have like maybe a one-off teacher who was not as particular about your subject. Almost all teachers, they were always well prepared. When it came to the classes, there was never a moment when our teachers were not prepared with enough handouts. So, I graduated with my bachelor's in physics in 2013, in 2013. So of course, the best college award came to Miranda House many years after that, about 4 years after that. But even while we were there, we could see, the motivation that the managing body had and that our faculty members had in taking this college to places. And what was very instrumental, of course, in my development as a student and as a physics student was the curriculum. And, this is like a funny thing, like a funny quote that says that everything happens for a reason and the reason is called physics. But, while I was associated with Miranda House, I actually felt that everything that's probably happening on this planet is because of physics. Because if you look at the kind of courses we were taught over these 3 years, they ranged everywhere from classical mechanics to crystallography and thermodynamics. And this is something that when I tell my colleagues from a material science or a metallurgy background that, we were also taught some amount of crystallography and thermodynamics in our physics courses, they get very surprised because, and this is not like a small amount, we are taught a considerable amount of crystallography and thermodynamics. And each of these courses, they were all, the topics were covered in great depth. And as I said, the teachers were exemplary, so there was nothing to complain about, but there were a lot of topics. And this is, I think, very important to have a well-rounded curriculum. And of course, this is not something that, and I won't say this is something that we as students or faculty members essentially can control, but it is very, very important that in the formative years, in the years when your research interests, so when your scientific interests are just developing or just on the brink of, you getting interested in a certain topic, if the curriculum is well-rounded at that point and you get like a good flavor of different things. For example, we were taught everything from astrophysics to nuclear physics to quantum physics to classical mechanics. And at that moment, it did feel at times that there was a lot of stuff going on and probably no clear direction as to where, we should be going. But in the hindsight, it was very important because this essentially formed the basis of, deciding what I'd be interested in doing in the subsequent years. And it's very important to get a flavor of these different things. And I believe a very important role, as I said, comes from a well-rounded curriculum, and the BSc Honours Physics curriculum, I absolutely had no complaints with that. And when it came to Miranda House, it was not just about the curriculum, as I said. There was also a significant amount of scientific training and exposure. We had something called Miranda Tech, like a green technology park, which was equipped with, and it was very rare for like a graduation college, a college where only studies up to the graduate level were done, to have something of this scale and magnitude. And while I was associated with Miranda, this was still being developed, but now it's there in full form. And if you get an opportunity, sometimes you should definitely visit it because it has some of the state-of-the-art characterization equipments, solid state characterization equipments. And it is it looks like a park, but it has all relevant solid state characterization equipments. And that's very important because that's not something that forms a part of our curriculum. A lot of it is theoretical, and we do not, while we do have laboratory courses as well, a lot of it is not working on equipments like a scanning electron microscope or a transmission electron microscope. And while I was making this presentation and going through Miranda House's website, I realized that Miranda Tech, the Green Technology Park, has all these equipments, which is very rare to find even in some of the top academic institutions in India till date. In addition to that, there was a D.S. Kothari Center for Research and Innovation in Science Education. This was in association with the Department of Science and Technology. And there used to be people and projects from DST that used to come to us. And I myself have been associated with 2 summer projects with the D.S. Kothari Center, in which, if there was a PhD student affiliated with DST and they were working on, say, a given problem, a section of that problem was kind of allocated to graduation students like me. And we used to take care of that section. Then we used to report to the PhD students. So what that helps you to do is you get a flavor for research. You get a flavor for how research is done in an academic setting. You get your first exposure to research. But of course, you're also not solely responsible for a huge project. You're just like a small piece in that. So you are, and you also feel, when you are you contributing to a project in that way, and that project gets translated in the form of a publication, for example, you also get that feeling of euphoria that, during your graduation, you did something that constructively contributed to a project. So having platforms like these or centers like these within the academic institutions is also very important. In addition to that, there were various different centers because, it's not just physics, there's also zoology, botany, and there were different, centers for that. And then especially, this is something, again, that's very unique to Miranda House. There's something called a QuarkNet Nodal Center. And this nodal center is the base for all central universities that are based in the nodal center in the vicinity of the University of Delhi North Campus. And a lot of theoretical nuclear physics calculations happen here. So you can imagine the kind of scientific training and exposure that the students are being made available to while they're pursuing graduations. That's also very instrumental in kind of setting that tone in your head. And that is why a lot of students from Miranda House do end up, pursuing higher education or, pursuing a PhD, for example, in their fields of interest. That also is majorly credited to these kinds of trainings and exposure that the institute provides. While I was in Miranda, as I said, I was associated with 2 summer projects, but in addition to that, there was something called the DST-DBT DU Innovation Project, which is basically a project that happens on the Delhi University level. So this is under the Vice Chancellor of Delhi University, and it is in close collaboration with the Department of Science and Technology and the Department of Biotechnology. So this was something unique that was introduced in the final year of my BSc, and I was fortunate to be a part of an interdisciplinary team which had people from zoology, botany, physics, chemistry, mathematics, and we were all working on this project called Miles on the Yamuna. And what it essentially encompassed was, kind of evaluating the quality of water, the quality of soil, and the quality of vegetation in the vicinity of the river Yamuna. As you all must be aware that the Yamuna is extremely polluted, and there's a huge amount of industrial waste that goes into the river that tends to, infiltrate the soil with a lot of harmful toxins and chemicals and carcinogenic chemicals, which actually make their way into vegetables, and they are a major cause of cancer. They are major contributors to cancer cases in the capital, because for all the vegetables that we tested that come from the banks of Yamuna, we found high amounts of carcinogenic content. And what this project essentially taught me was to work in close collaboration with, very diverse colleagues. So there were people from, botany and zoology, who had a different perspective to things. There were people from mathematics who were helping us with data analysis. And then there were people from physics who were kind of devising the experiments. And then there were chemists who were coming up with ways to measure these toxins. So it involved a lot of background research. It involved a lot of crosstalk between diverse people. It involved a lot of interaction with riparian communities, the communities who were living on the, banks of Yamuna, for that matter. And when you talk to these people, you know a lot about essentially the living conditions there and what forces them to consume that polluted water, for example. But what it essentially sets in a broader perspective is the tone on how to conduct research on a given topic. So this was, for example, just something that we did for 6 months. And we had a lot of support from TERI, from DST, from DBT, and many other organizations while we were doing this. We were also made available equipment to characterize the quality of water, for example. But this is sort of your first full exposure to a small research problem. You learn how to handle equipment, which is also very important because each equipment comes with a cost, and there's of course a lead time. If you do not handle the equipment well, and the equipment fails or breaks down for some reason, there is a lead time before you can get another one. And you basically learn how to carefully handle equipment. You know the importance of field visits. You know the importance of interacting with people who live by, or interacting with the in case of, say, a scientific research, conducting good background research. And then you also learn data analysis because a large amount of data is made available to you. And you're looking at it for the first time, and you learn how to analyze and make sense out of that data, and convey it in a sense that can convey a bigger message. So these kinds of small projects, small internships, scientific trainings are, in my opinion, very, very important in kind of setting the tone right from your formative academic years. And that's what I wanted to drive through this slide. After graduating with my bachelor's, I did my master's from the Department of Physics and Astrophysics in University of Delhi. This was an intimidating course for me, and the curriculum was extremely tough. The evaluation was extremely tough, and there were times, I was always a very good student, if I may say so. And I was also, one of the rank holders during graduation. But when I moved to, my post-grad and doing MSc Physics from the Department of Physics and Astrophysics, that was a huge change for me. Not only were the subjects much more difficult, but everything had become much more specialized all of a sudden. And that transition was, of course, difficult. The evaluation was very difficult, as I said, and it took me some time to get used to it. But what it also teaches you is our skills on how you basically make a smooth transition, or make a transition from, say, a one way of doing things to a completely new way of doing things. And that transition, or that, transition from BSc, in which, as I said, it was more like a school in which we were given notes, and the teachers were very passionate about what they taught. So we had all the material available. We had all the material at our dispense during graduation. To all of a sudden, you are given, say, a list of books that you have to refer to, and then you're left by yourself. So there is, of course, at each stage of your life, I believe, a huge transition, and that transition teaches you. And this transition taught me how to, adjust to difficult situations and probably kind of adapt myself to new situations. In addition to that, there was, of course, a lot of hands-on training compared to graduation. Master's was much more specialized, and there was a lot of hands-on training. And then there was also a possibility to do a 1-year-long dissertation project, which I feel was the most, was essentially the stepping stone to my PhD, and which essentially convinced me that I could, I was passionate towards research, and I wanted to pursue a PhD degree after my master's. And for the same reason, I'd just like to, briefly touch upon the dissertation project I did as part of my master's. So my project was titled Study of Vanadium Pentoxide Thin Films for Solar Cell Applications. Basically, vanadium pentoxide is a thin film oxide. It's an oxide thin film. It's like a semiconductor film with a tunable band gap. By integrating vanadium pentoxide films with other oxide films and other organic films, you can basically make organic solar cells. So this was essentially, we'd always read about band diagrams and semiconductors and solar cells and how they work. And, for those people who are from the electronics background, when we talk about photodetectors, we go from, we work in a different quadrant. And when we work on solar cells, we are working on the fourth quadrant, for example, and then there's a J naught and then there's a V naught. Those are things that we used to essentially, till that point, I used to only know that in theory. But when I did this project essentially introduced me to the practical aspect of things. And it was very instrumental in teaching me that I was not as well, I'd say, I knew as much as I thought I did, because, when you are doing a course, there are a certain number of questions that come, and you attempt those questions and you perform well in the exams and you feel you know the subject. When I was doing this project, I realized at multiple times during my 1-year dissertation that I did not know enough. And I'd like to go, in the reverse chronological order in talking about what all the project taught me. First, it taught me how to do a proper literature review. I had also done this during my project in my bachelor's, but of course it was that time I was working as a team. And, when you work as a team, the work essentially gets divided. You're not the only one who's responsible for, a particular aspect. And even if you miss something, it's perfectly fine. But when I was doing the dissertation project, I was all by myself. So I learned how to do literature review. I learned how to research on a given topic. I learned how to read papers. That's also something that is not very straightforward, I believe, because there's so much information in the paper, but to be able to, look at a given manuscript or a given publication and find out the things that are pertinent for you, that is also a skill that's very important, I believe, and it saves a lot of time and it makes the work much more efficient. So I, of course, learned a lot of a lot on that front while doing the project. At the same time, I learned a lot about band diagrams. As I said, till that point, I only knew everything theoretically. But when you work with organic solar cells, a small change in the conducting oxide, so basically you're using a metal on one side as the contact and a transparent conducting oxide as the other contact. And then, you have these layers in between. These are called HOMO and LUMO layers, which are kind of analogous to your valence band and conduction band in semiconductors. And these are very sensitive to how you grow these films. So depending on on how you deposit these films, the properties change, the band gap changes, the position of the conduction band changes. There are defects introduced in the films. Depending on how or the thickness of the transparent conducting oxide that you're depositing, the band alignment between the two contacts changes. So it was very sensitive to the process. And till that point, I had absolutely no idea how band gap engineering was done. But this was my first introduction to how basically band gaps between two semiconductors or a band gap at a heterojunction is engineered to kind of realize the device operation that you desire. In addition to that, I learned a lot about solid state fabrication and not fabrication, I'd say, deposition and characterization techniques. For the first time, I used an E-beam evaporator. I had no experience of using like a proper deposition tool ever. And, we deposited all sorts of conducting films on flexible substrates, on glass, and so on. And of course, when you do things for the first time, it's you're learning new things every day. So of course, it's very interesting and it's very intriguing. So that was a nice learning experience. This was also the first time when I was, I saw an X-ray diffraction system for the first time. Till that point, I had no idea how an XRD system looks like. And at that point as well, we had technicians at the university who would help us with measurements. So I did not do the measurements by myself, but of course, from just seeing things in the book to actually seeing things physically, it makes a lot of difference, and it enhances your understanding significantly. At least for me, I am somebody who sees things and learns, and I only learn by seeing or learn by doing. I am more efficient that way. So the project was a great learning experience for me in that sense. Also learned about atomic force microscopy. Tried this was the tip of an like an AFM tip that we tried to image using SEM. So I got introduced to scanning electron microscope and how it looked. And then, during my dissertation project, I did not have the luxury of doing nanofabrication. And that's also something that I'll be talking about in the next slides. But the way we used to, fabricate our devices, or how our devices essentially looked like, was that there was this, this is the film. The brown thing that you see here is essentially your conducting film, or the absorbing film that would be contributing to your solar cell operation. And then on top here, you cover this area with like a chrome tape or a metal tape or a silver tape, for example, and that's what forms your contact. So these are like millimeters of sizes of contacts. And but since this was my first foray into devices, and when you test these devices in, say, a solar simulator, they work, and that also gives you like a good high. So I feel this was my first introduction to solid state deposition and characterization tools. And similarly, I am so sorry. Okay, I just wanted to convey something, but there is an issue with the animation. So I would just say that in this slide, what I wanted to say was I also learned a lot about data analysis. So if you can just look at like the dim graphs here, this was for the first time, I had some data from the technicians, and then I had to kind of analyze and make sense of it. I had to plot it. I had to learn to make sense of the data, learn to analyze an XRD data or an IV curve, for example. And this, of course, this is something that you do for the first time when you're doing something hands-on for the very first time. And this was my first introduction to essentially the world of semiconductors. And this 1 year-long project For me, more than what I learned, what was the most important part of the project for me was the fact that it kind of instilled in me the confidence that I could do good in research, and that research was something that interested me, and I was convinced that I wanted to, spend the next, say, 4 or 5 years working dedicatedly as a PhD student. And this brings me to the next part of my journey, which is when I moved from Haryana/Delhi to Bangalore for my PhD. And I pursued my PhD from Center for Nanoscience and Engineering. The abbreviation for that is CENS, which is at the Indian Institute of Science in Bangalore. And right from how the CENS building looks, if you visit IISc sometime, you would notice that this is one of the few colorful buildings on the campus. And it's a beautiful looking building, multiple colors, and you have this a building literally that's a little inclined and a little curved. So right from how different it looks to how different it operates, it is a different world inside IISc, I'd say. And if you look at the third picture here, it's a very blurry picture, and I'm sorry for that, but I wanted to put it solely for the reason that if you closely look here and you see those round windows, they're not essentially round. They're basically like a circle with a cut at the bottom. And these resemble silicon wafers. So I had, worked 1 year on like a solid state project, but I had absolutely no idea how silicon wafer looked like before I joined CENS. So right from the first day when I was given a tour of the building, I was told that, look at those buildings, they look like silicon wafers. And that's when I realized that silicon wafers looked like, circles with a small cut line at the base. So there's there's a lot that's different about this place than any other academic institution in India, I believe. And through the next slides, I would like to quickly talk about it as well. In CENS, in the Center for Nanoscience, we have a lot of diverse areas that we work on, ranging from electronics to materials to micro electromechanical sensors. These are literally, I don't know if you can see the small arrow here. There's literally a very thin, like nanometer size graphene that's suspended between the electrodes here. So it's essentially like a nano device. There are people who work on microfluidics, nanobiotechnology, neuroelectronics. You basically name it and you have it at CENS. And there is like a whole new world inside the department. And there are so many different people with very diverse backgrounds working as a team at the center. What CENS boasts of and what is something that fascinates everybody about CENS, I believe, is the National Nanofabrication Center, which is a 14,000 square feet of class 100, class 1000 clean room. So basically a class 100 clean room is, a room that has less than 100 particles of 0.5 micron size per cubic foot of air. So if you look at an air-conditioned room, it has about 5 lakh to 10 lakh particles per cubic foot air. But inside a clean room, inside a class 100 or 1000 clean room, for example, you have less than 100 or 1000 particles of 0.5 microns as compared to the 5 lakhs that you would see outside. So it's essentially a clean environment. And these are some of the pictures of our clean room. And our nanofabrication center is capable of routinely processing 4-inch silicon wafers, which you also see in the image here. This is basically a boat in which you see 4-inch silicon wafers. And there are also a handful of tools that can process larger, that is about 6-inch substrates. We have a lot of facilities at our center. This, for example, are some images from the lithography. If you look at lithography as one of the processes, we have, an optical lithography setup. We have, laser imprinting or laser writer. There's a laser writer. There's an e-beam lithography setup. So there is like, a spin coater inside a glove box. So you name it and you have it within the center, everything that you need to, basically enable nanofabrication of devices is something the center is equipped with. And similarly, there are equipments with tri-etch, there are wet processing equipments, there are deposition equipments. It's possible to also characterize your devices in line. So if you fabricate the devices inside the clean room and you are scared about contamination and you do not want to take the devices outside, and characterize them. There are also setups inside that you could characterize them. There are also in-house development, rooms within the, or bays within the clean room, in which you have tools that have been kind of assembled within the center. Those are tools that have been developed and assembled within the center. And I felt that this image, for example, is a great reflection of the capabilities of the Nanofabrication Center. And this is, using the nanofabrication tools. This is the IISC and the SENSE logo that has been kind of carved on a silicon wafer. And if you look at the dimensions here, this is about 200 microns. So this is about 200 microns here. And, this is essentially carved on silicon wafers using the nanofabrication facilities that are available at the center. Similarly, you see here a fully fabricated 2-inch wafer. And then if you look at a completely different dimension of the, the nanofabric, like the things that can happen at the NNFC or the Nanofabrication Center, you see this graphene device. Here, I think you can clearly see like a thin thread of graphene that's suspended between two electrodes. So if you look at the dimensions here, it's about 200 nanometers. So this is about 400 nanometers in length. And this is actually a nano device that has been fabricated at the center. And these devices are routinely fabricated by the research students there. It's also possible to do epitaxial growth. So basically, if you want to grow thin films on your substrate epitaxially. And this is something that I think the next speaker would be talking about in great detail. So in this presentation, I just wanted to introduce you to the center, to the facilities and the training that's available at the center that kind of transform you into a more confident and skilled individual. But in the next talk that I'd highly encourage you to attend, you will see a lot of technical aspects being covered as well. So of course, this is like an epitaxial growth reactor that my colleague would be talking about in the next talk. And this is known as a metal organic chemical vapor deposition reactor. And this is used for the growth of, for example, nitride films. So aluminum, gallium nitride films. And this is, a grown film on a 2-inch silicon substrate. In addition to fabrication, of course, you also need to characterize your devices. So you have the micro nano characterization facility called the MNCF. And you have the possibility to characterize your devices electrically. You have probers, you have semiconductor parameter analyzers, you have RF measurement setups, you have helium and nitrogen cooled setups, which can measure your current voltage characteristics down to 4 Kelvin. Then you have mechanical characterization possible, in which you have your AFMs, you have ellipsometry, and many other things that you can also do in the mechanical characterization setup. You have the possibility to do material characterization by using TEM. You can have SEM, you have FIB, which is focused ion beam. So transmission electron microscopy and scanning electron microscopy. And of course, there are optical characterization techniques, optical characterization setups such as XRD, FTI are also available at the center. So essentially, you have everything available under one roof. And when you have so many facilities at your disposal, of course, the possibilities are endless. And there's nothing that stops you from doing good research, I believe. So having good infrastructure is, again, also very instrumental in, honing your technical skills. And then, of course, you also have packaging labs. So you not only fabricate and characterize your devices, but you can also package your devices. So you have all the facilities that you need to package your devices into individual chips. For example, this is an absolute pressure transducer that has been packaged entirely inside this packaging lab. And again, this is a MEMS pressure transducer that has been packaged, and these are also commercially supplied. So we have all the, facilities to actually right from device design to epitaxy, to fabrication, to characterization, to packaging, right? The entire spectrum, there are all facilities available at the center to do whatever you aspire to do. In addition to that, the center also closely works with a lot of industry affiliates. So, here's a list of all the present and past industry affiliates that have been associated with SENSE. And not only do they provide MTech fundings, for example, but they also provide research projects or internship programs that you could enroll in, and you could work in these companies while you're pursuing your PhD or while you're pursuing your master's. And then you also have the possibility of, working with them after you graduate out with your master's or PhD. All these facilities that I talked about, they're not just reserved for, I'd say, SENS people. Even, students from universities outside IISc can access these facilities through the Indian Nanoelectronics Users Program. So they're also like open to the entire country. And there is like a procedure through which this goes, and all the information you can find on the INUP website, essentially. And the INUP also, keeps organizing training programs to, kind of acquaint people who do not know much about nanofabrication and characterization techniques routinely. So there was one that happened in March, and then there's also another one that's happening this month from next month, that's 17th to 27th of May. And you can freely register for this, and it's happening virtually. So you have the possibility of, enrolling for this and also knowing more about the nanofabrication and characterization techniques that I talked about. Now I'll just very quickly come to the work I did at SENS. I was supervised by two advisors, Professor Srinivasan Raghavan, who's a material scientist by training, and Professor Digvijay Nath, who is in electrical engineering, and then he did his PhD in semiconductor devices. And then I was also unofficially supervised by Dr. R. Muralidharan, who happens to be the ex-director of the Solid State Physics Laboratory, DRDO. And, when you work with such a diverse team, you are bound to learn new things. And working with these people meant that I was also a part of two different research groups, which had people from the electronics background, from the electrical engineering background. There were chemists, there were physicists, there were material scientists. So there was a large spectrum of people that I was working in, and a largely interdisciplinary team, which of course teaches you a whole lot. The research topic for my PhD was ultra-wide bandgap semiconductor heterostructures for UV optoelectronics. I did not want to go too much into the jargon, so very quickly I would talk about the work I did at SENS. Basically, sun emits in a range of wavelengths, ranging from the high energy UV radiations to the low energy infrared radiations. And if you look, so visible is what we see. And if you look at just the ultraviolet regime of the electromagnetic spectra, 95% of that is UVA, that is the wavelengths between 320 and 380 nanometers. 5% is UVB, that is 290 to 320 nanometers. And below the wavelengths of 290 nanometers, essentially, you do not have any, background from sun, because the ozone layer that surrounds the Earth's atmosphere, it absorbs all the wavelengths below 280 nanometers. So any detector or any photodetector, what a photodetector essentially is, that it converts an optical signal to an electrical signal. So when there's a light of a wavelength incident on it, there is, it kind of kicks like a carrier from the valence to the conduction band. There's a possibility of charge transport, and you could have some electric current in the circuit. And by detecting that, you can actually detect the light that's falling on your device. So basically, any light that falls below 290 nanometers, that is free from solar background. So if you see any detection on Earth for wavelengths below 290 nanometers, you know that it is coming from an external source. And therefore, detectors that operate in this wavelength regime are known as solar blind, because they're free from the solar background. And these detectors find a lot of applications. For example, in UV imaging, for example, this is a UV image of the sun. And you could see the solar flare. So where more signal is coming from is the region where the sun's hotter, the temperature is higher, there's more chemical reactions happening here, which are leading to emissions in the UV. Typically for these, imaging, what is presently used as technology is some silicon-based photodetectors, and you put a lot of filters on them. So silicon has a small band gap of 1 electron volt, so it is sensitive to infrared. But if you want to make it sensitive to ultraviolet, you have to put a lot of filters to suppress the infrared and visible absorption in silicon. And that is why you need a lot of filters. Also, silicon has a very small band gap, so it has a lot of leakage current, even without an external optical signal at room temperature. So for that, you need to also cool down your devices a lot. So that essentially leads to a large footprint and weight. And if you look at the breakup of the weight of, this is an imaging spectrograph that has a silicon detector. And if you look at the breakup of the weight, you would see that a large portion is contributed by the use of an external battery, filters, and cooling assembly, whereas the actual detector module is only a very small fraction of the total weight, which tells you that if you replace silicon with a detector, that does not need filters, that does not need battery, that does not need cooling, you can actually get rid of all of this weight and complexity, which is all something that's very technologically viable. In addition to imaging applications, you also need these detectors for detecting, for making wearable sensors that can be used to detect the amount of UV your skin is being exposed to, for example. And then they can also be used for an early detection of missiles. So the missile plume that comes has reactions that lead to emissions in the UV regime, and by detecting that, you can very quickly detect a missile emission. So for all these applications, you need a detector that is intrinsically solar blind. That is, it is not having any response in the visible or infrared. It's only having response in the ultraviolet regime. So silicon, for example, has response even in visible, because of which you have to use filters. But if you have a detector that is intrinsically solar blind, or which is not sensitive to visible or infrared light at all, and it's only sensitive to the UV regime of the electromagnetic spectra, you can get rid of the filters. Then you also want your devices to be self-powered. That is, you want them to have this detection operation or a finite current in the external circuit, even when you're not applying a bias. So basically, you should have like a finite field in your, the active region of the device, which sweeps away your carriers and separates your carriers, and then that leads to contribution of a current. So you do not have to essentially apply an external voltage or field to sweep away the carriers. In addition to that, you also want to have a low noise so that you can sensitively detect your signals, and you want high efficiency. I will not get into the nitty-gritties of this, as I said, but very quickly moving on to what makes some of these detectors, I think, intrinsically blind. What is the deciding factor here? It is essentially the band gap. So basically, if you see here, if you have a band gap like silicon, which is like 1.1 electron volts, which is somewhere here, as I said, it's sensitive to infrared. If you have a band gap somewhere in between, say 1.8 to 3.2 electron volts, you are sensitive to the visible region and you can have a visible detector. But if you want a detector that's, sensitive to just the ultraviolet regime, which is like 280 nanometers, like from here to other wavelengths below that, you need your semiconductor to have a band gap higher than about 4 electron volts. And that is where a semiconductor known as aluminium gallium nitride, or semiconductors of the gallium nitride family. So just like silicon, gallium nitride is a semiconductor that has a band gap of 3.4 electron volts. And then there's another semiconductor called aluminium nitride, which has a band gap of 6.1 electron volts. Now you can form alloys of GaN and aluminium nitride. And these aluminium gallium nitride alloys can have a tunable energy band gap. You can essentially tune the aluminium mole fraction in your AlGaN alloy. And using that, you can actually tune your band gap from 3.4 to 6.1 electron volts, and essentially tune your wavelengths from 365 nanometers down to 200 nanometers. So basically now your devices, if you have your devices using gallium nitride or aluminium gallium nitride as a semiconductor, it is no longer sensitive to visible and infrared, and it's intrinsically visible blind. Similarly, there are other wide bandgap semiconductors such as gallium oxide, which could be used for this purpose as well. The gallium nitride, you must have heard this semiconductor. You must have heard this name before, because it was the same semiconductor that was awarded the 2014 Nobel Prize in Physics. And it was given for the development of blue light emitting diodes. So why this development was so important was that red and green LEDs existed already. But to make a white LED, you essentially need red, blue, and green LEDs. And blue LED, making a blue LED was huge development in this regard, because that enabled the white LEDs. And if you compare the lumens per watt, it has a considerably higher lumens per watt compared to fluorescent lamps and light bulbs, and it also has a much higher lifetime. And these solid state light emitting devices are also very important for energy saving. So it was a huge development, and that is what led to the 2014 Nobel Prize in Physics. And this is the same semiconductor device that I used for during my PhD. Also, as I said, you want these devices to have a field in the intrinsic region. So, you must have heard about Schottky diodes or PIN diodes. These are like very simple energy band diagrams. You have like a Schottky junction, for example. Here, this is like a metal semiconductor junction, and you see that there's a field here. Now, this field is enough to sweep away a carrier and get it collected at the contact. Similarly, in a PIN junction, there's always a finite field in the intrinsic region. So if there is, photon absorption happening here, and there are carriers generated here, since there is a field in this and this region, using a Schottky and PIN diode, you can enable separation of carriers even without the application of an external bias, which makes these devices self-powered. So by using AlGaN, you got rid of the filters. By using, a vertical device geometry, so we call these vertical devices, in which you always have like a field in the absorbing region. By using a Schottky or a PIN detector geometry, you can get like a self-powered operation. Basically, you can have devices that can detect a UV signal even without an external bias, and you have basically gotten rid of the battery. So the two main challenges of having a filter and a battery, you've gotten rid of that. So that leads to considerable amount of saving in terms of footprint, in terms of cost, in terms of efficiencies, and so on. My work at Sense was, as I said, largely interdisciplinary, right from device simulations to bandgap engineering, because again, AlGaN, these are AlGaN-GaN junctions, are heterojunction devices, and they involve some bandgap engineering to get the best device performance, to device design. So basically the mask design to fabricate the nano devices, to growing thin films for my detector applications on Sapphire, which is the substrate shown here. This looks transparent, and I think the next speaker would talk about it, so I will not touch upon this topic here. So basically, right from simulation to bandgap engineering to device design to epitaxy of these films or growth of these thin films on Sapphire, to material characterization, to nano fabrication of these devices. This is an actual optical image of how the device looks. There's like a top P contact, a bottom N contact. This is like a ring. The top P contact has these fingers to kind of separate and collect your carriers. Then to characterizing these devices electronically and optoelectronically, and then finally packaging them into linear arrays. I did all of these things as part of my PhD. So it was essentially the entire spectrum for ultra-wide bandgap based optoelectronic devices. And we essentially touched upon all the aspects, and all of that work was done at Sense. And one of the highlights of my PhD work is realizing an AlGaN detector. If you look at the star here, this is a zero bias efficiency. So basically EQE is an external quantum efficiency. And at zero bias, that is without the application of any external bias, we have a zero bias efficiency as high as 92%, which means that 92% of the carriers that are getting absorbed, and that are 92% of the photons that are getting absorbed and that are generating electron hole pairs in the devices are kind of contributing to current in the external circuit. So it's a very high efficiency, and this is the highest number that has been reported for ultraviolet detectors till date. While we were working on this, we were also given the opportunity to work on a perspective, an article in which we were, supposed to talk about where we see ultraviolet detectors based on aluminum gallium nitride going in the near future. And, this schematic kind of compares how complex a silicon-based detector is compared to how simple an AlGaN-based detector can make the entire system. And in this, we were kind of trying to compare the number of publications on photodetectors with years. So we see that, there are a lot of publications. So with, over the years, the publications on AlGaN-based photodetectors have been increasing exponentially. But if you now look at the kind of work that's being done, most of the work that's being done is at a very primitive stage. So, it's limited to either epitaxy and device fabrication, but for actual devices and, to be able to put them out in the market, or to really have devices or systems that you could use to measure an external UV signal, for example, based on AlGaN detectors, there are only like a handful of companies that are doing that. And there is not a lot of research effort that's also being put on important topics, such as, are these devices reliable? So of course, like I predict, I showed you a result in which I said I had 92% efficiency, but how reliable were my devices? When I subject them to a large UV stress, or if I put them in UV for long enough, or if I, subject them to some sort of an aging or some sort of a climatic test, are these devices will the devices survive the test of time, for example? Also, what is very important is that individual devices cannot do anything. You have to have a large array of these devices and you have to integrate it with circuits. So that is what we talked about in this perspective, that there is still a long way to go. We are still at a nascent stage and there is a long way to go. But what we are very proud of, especially at SENSE, that we have covered a lot of these things. We are also one of the first research groups to have worked on the reliability of these devices. We have also demonstrated a proof of concept linear array for these devices. And of course, that sets a nice platform for any company that wants to take the technology that we developed as part of our PhD projects, and that they can take it, of course, and develop it and classify it for an actual device. Again, as part of my PhD, this is again the work that I was talking about that was recently published, and it was also featured in the Science Today news. I was fortunate to have a good number of publications. I was also fortunate to have the opportunity to present my work at multiple conferences. So I happened to be there for at least 8 to 9 international conferences. And I was also awarded the Best Poster and Best Student Paper Award for 2 consecutive years at the Electronic Materials Conference, which is a very prestigious conference in our field of research. And in 2021, one of my papers was also the top cited paper award. So of course, the amount of I'd say the kind of training that I received from SENSE helped me not only to network by going to multiple conferences, but also helped in establishing a good curriculum vitae, for example. And that's very instrumental when you apply for, say, a job after your PhD, be it an academic position or be it an industrial position. You need to have like a good CV, because that's literally the first thing that's screened. In addition to, of course, work, I was also associated with a lot of co-curricular activities. I was a very active part of the Nanotechnology and Sensors Council, which organizes a lot of summer schools and conferences at the Institute. And I was very actively involved with that. As I said, I attended multiple conferences outside India, and that's very important for your personality development as well, because you learn new things and you learn how to adjust yourself to new environments, and you also learn how to present your work in front of a diverse audience. Not everybody might know what I am working on, but my point is to keep them intrigued throughout my talk. I also was a member of the editorial board. So those things essentially, while you might consider we as PhD students, we have so much work to do. We do not put a lot of emphasis on gaining these sorts of experiences, but I believe these are very important because they shape you as an individual. And whatever you learn, the kind of experiences you gain from these all these sorts of things that you pick up other than your work, they reflect in how you conduct yourself in front of your interview panel. And that's also something that's very important. It's not enough to know a lot of stuff, I believe. It's also very important to be able to convey it to the interview panel and to kind of, be a confident individual in general. I'd just like to take like 1 minute to talk about SENSE and how it's extremely instrumental also in technology development. So there are already a lot of research projects from SENSE that have been converted into actual devices. So these are some images, and you can find all the information on the SENSE page. For example, this is an EnviroBot. This is a gas sensor array called AirSense. Pacho devices, it's a handheld device for managing diabetes, and it's the only device in the world. And this is something that we as, SENSE students are very proud of, that there are some research students from our department who have actually conducted research, and they have translated their research into an actual device, which is one of its kind in the world, to produce, to perform different sorts of tests for managing diabetes, which are very instrumental, especially if you want to prevent conditions like diabetic neuropathy and so on. Even during COVID, for example, my advisor and some of the other students and faculty members from the institute developed a ventilator prototype, and that was in association with the company. So they developed a prototype all within the environment during COVID. This was during the peak of the COVID wave, and these 5 or 6 people were coming to department every single day to work on these. So it requires a certain sort of commitment, and that's always there. And I feel these things are very important. because if you have the facilities to be able to translate it to something that can benefit mankind, it's extremely, extremely important. In addition to that, my advisors have also come up together with MITI. They have set up a development line gallium nitride foundry called GIGI. It's called the Gallium Nitride Ecosystem Enabling Center and Incubator. And you must have heard about this in the news. Gallium nitride, as I talked about, is not just important for photodetector applications like what I did for my PhD, but it is also a very promising semiconductor for power electronics. A lot of the power, gets lost during conversion. And currently silicon-based power converters are what are being routinely used. But if you replace silicon by gallium nitride, there is a promise of about 25% of energy savings. And, this translates to 125 megatons of reduction in the carbon dioxide emission worldwide. So as a society, we should all move towards a green economy, and gallium nitride devices are the way to go. And that is why I think the government also invested in GIGI, which is a brainchild of my advisors. And right from fabrication, characterization, packaging, testing, reliability studies, everything is done within Indian Institute of Science under the same umbrella of GIGI. And recently, there were also multiple minister visits to, look at the progress that the company is doing. And if you see this person here, he's one of our colleagues. He is one of the research members of our research group who graduated from IISc, went on to do a postdoc outside India, and then came back and as one of the co-founders for GIGI. And as part of GIGI, they have also, set up a small, they've also incubated a startup called Agnet, which is gallium nitride devices for something technology. I'm sorry, I'm forgetting the name. But all sorts of, right from fabrication to characterization to testing, everything happens in IISc under the same umbrella of GIGI and Agnet. And that's a huge thing to come out from an academic setting, I believe, because then you're also kind of, equipping students with enough skills that are requisite for an industry. Very quickly, and I don't want to repeat myself too much, but my major learnings from my academic training were diverse technical skills, the ability to draft and defend research proposals and projects, which is very important. If your advisor gives you the opportunity to draft projects, as faculty members, I think you should give your students, the possibility of drafting a project for you, because in that process, they also learn a lot. You also learn a lot of time management. You realize the indispensability of concerted team efforts. You know that you work as an interdisciplinary team, for example, our team that we had. And you know that a team effort is important. I cannot probably be doing all parts of my PhD work, and I might be dependent on somebody else for one optimization, for example. So I have to work together as a team. You also have to actively collaborate. Similarly, you go out and attend conferences and gain some visibility in the scientific community. And I believe this is a very good time to do that during your PhD. A lot of people are hesitant to go out to conferences. I think it's very important to go to conferences and meet new people and listen to the the myriad of talks that come there. You also kind of, when you attend these conferences, you stay in touch with the recent developments. A very important thing that SENS taught me, I don't know if all academic settings can teach it, is to rise above hierarchy. We did not have a hierarchy-based setting, and at SENS, for instance, when you are a part of a group meeting, it does not matter how senior a faculty member is. If I do not agree on a technical level with what the person is saying, I have all the right to respectfully disagree with what the person is saying. So that is something that SENS has taught me, and that's very important in an industrial environment, because even now in my present company, for example, I have people working in my team who are 20 and 25 years senior to me. But there are times when I have technical disagreements with them, and that is something that SENS has taught me, that I can be respectful and still disagree with them and make my point. And that brings me to, I think, the most important thing that my PhD and my prior academic trainings taught me were interpersonal skills requisite to direct seemingly contrasting opinions into a coherent direction to enable realization of a technologically relevant end goal. And I want to spend a minute on this, because at the end of the day, irrespective of whether you're handling a academic project or an industrial project. You want to, there would be people with different opinions on how a certain thing must be done. There might be people who, might want to place different importance on different aspects of the project. As a team leader or as a team member working on that team, you should have the ability to kind of direct different contrasting opinions into one direction, because the end goal for you should always be the realization of a technologically relevant end goal. And you should know how to direct all these different opinions coherently in a very constructive manner to your project, and not let it affect you destructively, because that's also something that can happen when you have so many different people contributing to the same effort. As they say, too many cooks spoil the broth. You should have the ability to not let that happen and kind of, direct the entire effort in a very concerted way. A very funny thing, and I found it very important to share this again as well, that I also learned a lot of aesthetics from my advisors, and I will always credit them for my presentations. I have been told that my presentations look decently well aesthetically, and that's something that I learned from my advisors. This is how I used to, plot my curves before joining my PhD. And this is like a recent graph that I plotted. So I think you could, you can clearly see the change in the aesthetics. And a lot of people don't put enough emphasis on this, but it's very important when you're making a presentation. I think to drive across your point, it's very important that you have good graphics. You have like good, aesthetically pleasing graphs, so that people kind of get attracted to your graph and pay attention to it. If you have something like I have on the left side, I do not think people will pay much attention to it. And the legends itself are not large enough so that, somebody can see it from a distance, for example. And these are things that I learned from my advisor, and I'm forever indebted to both of them for that. Similarly, if you compare my CV, I just wanted to put it out there. This is how my CV looked like when I joined my PhD, and this is like a recent version of that. So as I said, your CV is the very first impression that you make whenever you apply for any position, be it academic or industrial, and you want it to look aesthetically pleasing, and you want it to be concise. It should have all the information about you, while also not being humongously long. And that brings me to the final leg of my presentation, which I will not take too much of time. For early this year, I made a transition to a different corner of the world, in Villach, Austria, to Infineon Technologies. And in the interest of time, I will not talk much about what Infineon Technologies does. It has 50 years of illustrious, it's one of the leading semiconductor companies today. And it started in 1970 as an extended workbench. And in 2021, it's a new fully automated fab with everything done by robots. The wafers are not touched ever. I recently had the opportunity of, visiting the fab for the first time. And I was amazed by how impeccably everything is done. The wafers are not touched by human hands at all. So that's where we stand at Infineon in 2021, and we routinely process, 8-inch wafers. I will show that, but these are the different areas basically Infineon works in. I will skip all of this. This is basically the campus. This is the old campus, the new ones being constructed. So I don't have a fresh image of that as of yet. But these are all the fab buildings, and there are about 12 buildings over which the entire fabrication facility or the clean room is set up. This is one of the rare clean room images that I could find on the internet. Unfortunately, due to confidentiality reasons, I cannot share most of these images, most of the images that I have. But this is one of the images I found as an open access. And if you look at this is something that I definitely wanted to show you the magnitude of things that are being done at Infineon. This is a wafer carrier which has 12-inch wafers. And it literally looks like a 12-liter pressure cooker. It's huge. And it has some 25 12-inch wafers that are routinely processed. And this is again an old picture because you do not see the robots here yet. But now there are robots to handle all of these wafers. So there are levers that pick these wafers up and load it into the tool that never touch human hands. So there's no chance of contamination. Before I end, what I want to share in like a minute is what I do at Infineon. I have transitioned from optoelectronics to power electronics, and I work on gallium nitride-based power devices. I work in a team called PSS. It's called Power Sensors and Systems. And basically, it targets two basic applications, IoT and big data, which is not something I do. But this is something more that falls under my purview. It's the energy efficiency department, where we basically work on efficient power converters based on gallium nitride. And I work there as a technology development engineer. It's a very R&D position. I do not miss my, the research work, the hands-on research work that I used to do as part of my PhD, because I'm still doing almost the same work. And my job is to develop technology, to release technology up to a certain point so that it can be picked up by the production, and then it could be, released to whatever projects and companies and so on. So the major goal behind doing all of that is to enable further energy savings, like I highlighted in one of the initial slides, and to help reduce CO2 emissions. That's one of the major goals of Infineon, that we want to move towards, a cleaner, greener world. And if we, quickly look at where we stand in terms of our market position, in terms of power, we are the number one semiconductor company. In terms of automotives as well, we are the number one. And in terms of microcontroller-based devices, we are number 3. And this is based on the Omdia and the Strategy Analytics reports of 2021. So this brings me to the end of my presentation. I think I just wanted to say that when you apply for an industrial position, you need an industrial resume, which should not be more than 2 pages, which is also something that you should keep in mind. And preferably, you should have an ATS ready resume, which means that it's a resume that can be detected by the AI. So when your resume screening happens, if you have an AI-ready CV, it's much easier for the artificial intelligence of your company to filter your CV out, and you have more chances of getting screened. So that's also something that I think the students should work on, and the faculty members should encourage their students to work on preparing a good industrial resume if they are interested in applying for a position. You should always have a good, coherent, concise 15 to 20 minutes long presentation of your work. It could be your master's research project or any courses that you took during your master's or your PhD research project, but you should have a small presentation of your research work. You should always, always, always have adequate knowledge about the company. This is something people do not pay enough emphasis on. Whenever you're going for an interview, you should know enough about the company. You should know enough about the team that you are interviewing for. You should know enough about the position that you're interviewing for. And you should evaluate yourself on the prerequisites that the company has set to see if you are eligible for the position or not. You should be willing to work as a strong team player. If you are somebody who works well in an independent setting, industry is not for you, because it involves a lot of crosstalk, a lot of interaction with people. And most importantly, it's very, very important to have a considerable amount of self-confidence, which I feel all of the people lack, because in most of our academic institutions, not a lot of industry interaction happens. Even even with SENS, and there was a lot of technology development going on, and our professors were also kind of coming up with the gallium nitride foundry. There were also a lot of industry affiliates, but still, it's possibly also a lag on my part, that I did not have a considerable amount of industry experience, because unlike universities in Europe, where the PhD research projects are typically funded by industries, for example, we do not work very closely with industry, so we do not know how the industrial setting works. So a lot of times people are not very confident about themselves, and they also have this misconception that if there are certain prerequisites for a job, they should know everything. That's not the case at all. I come from an optoelectronics background and do not know much about power electronics. And ever since I've joined, I have been made available a large set of trainings to get accustomed to this new environment. The transition could be easier for somebody who knows everything, but even if you do not know, I would highly encourage you to apply, even if you have some set of relevant skills for that position. You do not need to know everything. And I would definitely want to take this opportunity to bust that myth. And I think with that, I'd just like to end my presentation. Thank you so much for your time, and I am open for questions. I know that we do not have a lot of time, but my email address is mentioned here. So even if I am unable to take your question now, I could take this. You could always send me an email. So thank you, and please feel free to ask questions.
Thank you, ma'am, for enlightening us with illuminating presentation, which was a very detailed and graph presentation. There are some couple of questions that have been posted in the chat, so we'll address those. One first question has been asked by Rakhi Wazgi ma'am, the HOD
Mhm.
of computer department. Her
Yeah.
question is that it's a non-technical question. She's been saying that exploring new domain of technology is somewhat a very bit challenging task. How to overcome and simplify this task?
Yeah. So it's of course a nice question, but I would say the easiest way to do that is to do literature survey. Even if it's like a new technology, there might be something that has been done on the same material system before, or a similar sort of a work that has been done on another material system, for example. Or there could also be other aspects. Of course, you could always break a bigger research problem into smaller aspects. For example, when it comes to gallium nitride based devices, the problems can come from design, the problems could come from epitaxy, the problems could come from multiple different issues during nanofabrication and so on. So you could break your problem into smaller solutions, for instance, and tackle one problem at a time, and then you might be able to find help from the through literature research. And another good way to do that also is to get in touch with people who are kind of the masters in that field, I'd say, the leaders in that field, because of course their inputs is also something that can considerably accelerate your progress on a new domain, for instance. Yeah. Okay. I can see the questions.
Yes,
Should I?
there are a couple of there are a couple of
Yeah,
questions posted by Amuli Bezare ma'am.
yeah. I'll go
First
through
one
that.
is okay, yeah.
Yeah, I can see it. Sorry, don't worry.
Thank you.
Okay, so what she wanted to ask is, could you discuss the key points to be in a 2-page resume? Yes, there are also a lot of resources available online that I would highly recommend you to check. There's a website called Cheeky Scientist, and I can kind of enter that here, which gives you some good pointers. A lot of the information that's there is paid on the website, but there is also a lot of free source information or open source information available there. But just to answer your question very quickly, it should talk about your academic background, of course. It should mention your relevant skills. It should give enough of your contact details. You should, put your LinkedIn, you should put your email addresses, your contact numbers, all on one small column, your Google Scholar, if you have one, for example, and so on. Again, for industrial positions, I think there's one point that I forgot to mention and that I would like to mention now, that you should, I'd highly encourage you to have set up a good LinkedIn profile. Whatever your achievements are, whatever you're interested in, whatever your expertise and skills are, it would be good to list it nicely on your LinkedIn, because that's also something that recruiters see very often. Could you discuss? Okay, yeah, that's that. And then you could talk about your research papers. You could talk about any conference presentations that you've made, any awards that you have received. All of that's possible to include it in a 2-page resume. So yeah, you can do all that. Okay, the next question is, what is the role of Industry 4.0 with IoT? I am sorry, I did not get this, and I'm not very, I don't know how to say it. I'm not very good with IoT questions. I'm not very accustomed to this. I've not read much about it. So I'm really sorry, but I won't be able to answer that. Okay, yeah. So I think these were all the questions.
Yes, thank you, ma'am, for addressing those couple of questions. It was quite mind-opening for all the PhD faculties who must have got a good insight for a wide-reaching and a wide-ranging career opportunities for the substantial development for their career enhancement. Thank you so much, ma'am.
You're most welcome.
Moving ahead, I would like to request the HOD of Electronics Department, Dr. Adi Thakre sir, to present the memento to express our kudos and gratitude towards the hardworking and the young stalwart, Dr. Anisha Kalra. I would like to request her to present the memento, and we will have a photo. I would like full size it. Screen पर ही Ma'am, it will be great if you will turn on your cameras too, so that we can have a nice picture.
I am actually at, so there is
Okay.
some internet
Okay.
issue at my place. I'm at a very odd
Okay,
position.
absolutely fine. Absolutely fine.
Yeah.
I request other participants to turn on the camera so that we can have a snap.
Yeah, I could share my cover screen. Give me a sec.
Yes.
Yeah, that's okay. Yeah.
Thank you, ma'am. Thank you, all the participants.
Thank you so much. Thank you so much.
There's a small announcement for all the participants. Our next session will be starting shortly. And for the next session, our speaker is Shashwat Rakkantiwa, North Gloria State University, USA. So please stay with us. Thank you so much for the first session.